get started and hope that more people will show up as we move on. So it's my pleasure to introduce Shuo, who's right now a postdoctoral researcher with the University of Pennsylvania with the Department of Electrical and System Engineering, working with George Tapas. Before that, he was with Caltech, working with Richard Murray, and finished there his PhD. He will present a seminar on data-driven optimization under distributional uncertainty. Many of us are working on similar topics. I've seen a glimpse of that. It's a very interesting methodology to dealing with uncertainty and decision making. His research expertise is actually in rigorous frameworks for data-driven decision making and enabling the reliable and efficient operation of network systems. They have some work on interesting transportation systems that I actually will see today. Among his accomplishments, he is the finalist of the Best Student Paper Award at 2013 ACC and Open Control Conference. With that, thank you very much for being here, and I look forward to your talk.
Right, thanks for the introduction. So today I'll be talking about my work on data-driven optimization under distributional uncertainty. So first of all, I'd like to say this work is mostly motivated by the recent advent of Internet of Things. So simply put, this is my one slide introduction of Internet of Things. So just think about it as a network of physical objects, ranging from smaller things like your personal devices to larger objects like vehicles or even buildings. So the nice thing about the Internet of Things is that it allows objects to be sent and controlled remotely across the network. And the scale of the Internet of Things is, as you have already seen, growing very rapidly. And this is some prediction from a few years ago. It says by 2020, there are going to be about 50 billion devices on this planet, and that's about almost 7 devices per person. So, my background is mostly control and optimization. So from my perspective, one of the questions I try to ask is what this Internet of Things can bring. What opportunities can this bring to control and optimization? And as a person who actually use Internet of Things. So first of all, I would claim that the Internet of Things bring us more sensing, or in other words, it brings more data. It allows us to see the system in a much better way. So on this chart, I'm showing this data set, which is a taxi data set, which actually also including Uber trips in New York City. So you can see it's this relatively large data set, about 200 something gigabytes. And this records about 1 billion taxi and Uber trips in 6 years. And this is actually very detailed set of records. For example, it includes pickup and drop-off date times, travel time, location, distances, and so on and so forth. One thing you may immediately use of this data set is you can just do visualization and see, like historically, what the passengers' demand looks like. And the other aspect is control. So since we can now connect all these objects under control to a network, we now have more control freedom to all of these objects remotely. So for example, smart home appliances, you can now control for example, the temperature of your refrigerator even when you're absent from home. And also in the context of cities and transportation, there are connected and automated vehicles, there are wireless traffic light control, and also smart buildings. So now with the Internet of Things, in the context of cities, people have envisioned the concept of smart cities. So to some extent, you can think about the smart city consisting of 2 components. One is the Internet of Things deployed to the city as a part of the city infrastructure that gives you a lot of data about the city. And the other component is, for sort of the brain of smart cities, is the control and optimization algorithm that makes use of the collected data to make decisions, either in real-time scheduling or long-term planning for the cities to improve certain metrics, like people's life or efficiency, other things about the city. So from a research perspective, over the past years, there has been a lot of investment investment in smart cities, starting from the government, and then there are a lot of either federal agencies or places in industry also getting involved. So one particular project that partly funded my postdoc research is this project called Terraswarm. So just in relation to the UTC, this Terraswarm is jointly funded by DARPA and a few industrial partners, which includes United Technologies. So here's just a brief overview of this Terraswarm project. So I would say this project even started before the concept of smart cities got popularized. So I would say this essentially says the entire procedure of turning data into decisions. So on the outer layer, this is the layer called the swarm, which is the physical sensors, and at this layer it deals with the problem of how to efficiently collect data. And then the next thing you need to think about is how you transmit data, hopefully to some cloud services, to where the computation that makes use of this data happens. So I'm mostly dealing with the computational part. So just to be more specific, here are my general research interests. So my general research philosophy is to develop fundamental algorithms that are motivated by important applications. So currently, I mostly use tools from optimization, in particular complex optimization, control theory, and some statistics. And my application areas are mostly two. One is energy, in particular power systems, and the other one is the transportation network. So I have done a lot of various research topics in the past, but generally speaking, those topics fall into the area of stochastic systems, system with uncertainty, multi-agent systems, and also network system with dynamics. Okay, so just to get a little bit more detail, so I won't go through all the topics, but these are some of the specific things I have done in the past. And today I'm going to talk to you about this data-driven optimization, which is what I would claim a rigorous way of turning data into useful decisions. So I would like to start by giving you two motivating applications. So the first one is in the context of the power systems. So the problem is, generally speaking, how to integrate wind energy efficiently into the power grid. So many years ago, most of the generators in the power grid are powered by conventional sources like fuel, coal, nuclear even. Right? So in recent years, there has been a lot of growing interest in integrating renewable energy sources into the power grid. Things like wind and solar. So it doesn't really take you too long to see that the challenge of integrating these renewable energy sources is, like wind and solar, is that they are highly stochastic. So if the wind doesn't blow on this day, then you get zero power output from your wind farm. So on the right of this slide, I'm plotting the wind energy data, and I think this is somewhere in Canada, on 5 different days. And you can see that they vary quite a bit on different days. So now here comes the question: how do we integrate this kind of stochastic energy sources into the power grid while still providing some kind of reliability? So one mitigating solution that people have proposed is to insert storage devices into the power grid. So you should think about the storage devices in a more general sense. So they include conventional batteries. But more recently, people have also proposed to use data center as a way which serves as some kind of buffer, which behaves like a battery, right? Because you can kind of decide how fast the servers run in the data center. But anyway, we don't care about how the storage devices are implemented. And my question here is to ask how to allocate the available storage device into the power grid. And the goal is to maximally utilize the wind power generation. Right? So if I have, let's say, at this moment, I have more wind power generated than I'm currently using, then I could store the excessive power generation into the storage devices and then make use of the stored energy at a later time. And then here's the, you can imagine intuitively that you may want to, let's say, insert more storage to the places where there's more uncertain generation, where there's more wind power. But my research question here is how we can do this in a rigorous fashion. So this is an example from power systems. The second one is coming from transportation. So here is the problem in the context of ride sharing in cities. The fancy name, but just think about Uber and Lyft. So on the left, this plot shows the average wait time of Uber trips in New York City. So you can see different colors on the map. The darker the color is, the shorter the average wait time. Okay. So you can see across the entire city, there's some variation in terms of the average wait time for the passengers. And as it turns out, if one looks into the data, it doesn't take long to find out that the reason behind this is there's a big mismatch between supply and demand. And here's supply, meaning the available drivers to pick up passengers. Okay. So now, well, intuitively, you may come up with a solution that tries to move drivers to serve available passengers at a different area. Right? But since we cannot move cars instantaneously in time, it only helps if you can actually predict the passenger's demand before the demand is actually generated. Okay. So now we make predictions, and hopefully by making use of historical trip data. But now the thing is that how would you actually rigorously make use of data to make predictions and ultimately improve the quality of service for the passengers by controlling the flow of available vehicles. So let me get a little bit more mathematical. So if you look at both of these problems, there's a common feature. The first one is that you're solving some kind of optimization problem. So for example, you want to minimize the average wait time of the passengers, you want to maximize your utilization rate for the windmill. So it's an optimization problem. But the second feature of both of these problems is that there is some underlying stochastic phenomena that is part of the cost incurred. So mathematically, I'm just going to note this cost by a function f, and this function f depends on two things. So one is my decision that I can make, for example, my allocation of storage devices, and some random variable theta. So for example, wind power generation. So one straightforward formulation of this optimization problem in the presence of stochastic phenomena is that I want to minimize the average or the expected value of the cost function by making the best decision. So here, by taking the expectation, one implicit assumption that you're making is that you actually know the exact distribution that governs the underlying stochastic phenomena. Then that's called the D. However, you can imagine for complex phenomena, like wind generation, like passenger demand, it is not always that you have the exact distribution. But instead, what you have is data. But formally, these data it can be considered as random samples drawn from the underlying unknown probability distribution. For example, you have wind power generation on different days, and you can think about the profile on one day as one sample from the underlying probability distribution of wind power generation. So now the question is how we should make use of the samples with performance guarantees and also a computationally tracked way to make decisions. So in the past, there are two major ways to make use of the data available. So the first one is, I'm just going to replace the expectation with the sample average. So in other words, you're replacing the exact distribution with what's called the empirical distribution, which is just a fancy name for histograms. So this is a simple formulation. So computationally is amenable. However, the difficulty here is that it doesn't give you very strong performance guarantees. So far the best guarantee that you can have with this kind of approach is as my number of samples grows to infinity, my solution will approach to my optimal solution, assuming that I know the exact distribution. Some kind of the convergence result. Just law of large numbers. So however, this kind of conclusion doesn't tell you, it only tells you qualitatively that if you have more samples, then you can get a better result. But let's say now I know that I have 10,000 samples and want to get some quantitative characterization on how much performance guarantee I can have by this number of samples. So in terms of that kind of guarantee, another approach that people have came up with in the past is robust optimization. So here the modeling approach is different in the sense that instead of treating the underlying phenomena as being modeled by a random variable, the method treats the underlying phenomena as a deterministic parameter that varies within an ambiguity set. So once it's generated, it's anywhere within the ambiguity set, and the samples is just it's treated as also to be anywhere in the set. So that means I can actually try to construct this ambiguity set from all my samples, and the way it is constructed is to let essentially almost all the samples to lie within the set. Okay. So things like maybe depending on your confidence level, depending on modeling approach, it could be I want 99% of my data to lie within this set. And then I'm going to take a conservative approach to do worst case optimization. So I'm going to solve a min-max problem where the max is the worst case parameter within this ambiguity set. Okay. So this gives you some worst case performance, but the difficulty with this problem is that it can be extremely conservative, because it essentially discards all the distributional information about the underlying stochastic phenomenon. Well, the natural question that one can ask is it actually possible to still maintain this kind of uncertainty while still preserving the distributional information that was originally present in the underlying stochastic phenomenon? So here's the solution to it, which is to quantify the uncertainty using what's called distributional uncertainty. So it's a fancy name, but really what this distributional uncertainty is just an ambiguity set. But instead of a set that tries to cover the real parameter, it's a set of probability distributions that tries to cover the true probability distribution. So here, there's no assumption on the type of distribution within the set. So it could be continuous, it could be discrete, it could be Gaussian, it could be uniform distribution, it could be any distribution. So I'm not doing parameterized form of the distribution. And the only requirement with the set is that the true distribution needs to be contained in the set with high probability. So informally, if we think about it's the true distribution as the uncertainty, then this is the uncertainty around that uncertainty. So that's why I avoided using uncertainty to denote my probability distribution using the stochastic phenomenon. So now we can still do this worst case optimization by the following formulation. So here I'm still trying to solve a min-max problem. Okay. Well, compared to the original problem, which I assume to know the exact distribution. So here, the important thing to note is that this max is over all the distributions that lie within this ambiguity set capital T. So if we focus on this inner maximization problem, that's essentially the problem of finding the worst case distribution within the ambiguity set. Okay. So let's not worry about the computational tractability of this, but if we can actually solve this problem, right, then we not only preserve the distribution information like we did in the sample average approximation, but also we have strong worst case guarantees. And by the way, this also subsumes conventional robust optimization because it turns out that if I only specify the support of the distribution when I define the set capital D, then that actually reduces to conventional robust optimization.
So how do you enclose all the distributions into?
That's my next slide.
Okay.
So there are several methods for doing this, but roughly speaking, they belong to two classes. So the first class, which is not what I'm going to talk about today, is based on some metric or pseudo-metric that is defined on the space of probability distributions. So an example of a pseudo-metric would be K of divergence. So here, the way that the set is constructed is to construct a metric ball or pseudo-metric ball that is centered at the empirical distribution. Right? That's your histogram, which you can obtain directly from your data. And the radius of the metric ball is chosen to contain the true distribution with high probability. And this radius is, you can actually bound this radius by result from a classical probability theory. So I won't go into the details. So first of all, you can notice that the advantage of using this method is that I don't lose any information about my data set because the set is defined as something that is centered at my empirical distribution, which is the exact characterization of my data set. But the disadvantage, as it turns out, if you actually go down the path and try to solve the distributionally robust optimization problem, the size of the problem depends on the data set. So if you have a larger data set, then eventually the optimization problem we're trying to solve also becomes more expensive. So today I'm going to focus on the second method, which is to construct the set based on what's called generalized moment functions. Okay. So here, a generalized moment is just the exact value of any nonlinear function g that depends on a random variable. And I'm going to construct the set by a series of inequality constraints. Okay. So for example, this g can be the identity function, so that means you're specifying some information about the mean of the distribution. So if it's quadratic, then you're specifying some information on the second moment. Okay. So, and you can also go with other functions. For example, if I change this g to be the indicator function, and as it turns out, this actually specifies something about the tail probability of my distribution. So, there are various ways you can play to specify the information that you want about the distribution using this generalized moment functions. And again, like before, if you use results from classical probability theory, then you can choose kind of here is not the radius, but you can choose this generalized moment functions in order to contain the true distribution with high probability. Okay. So if you stare at this problem, right, as I mentioned, the inner problem is really to find the worst case distribution. Then you can imagine that the major challenge here is that in the inner loop optimization problem, where we try to find worst case distribution, we're essentially optimizing over probability distribution, which are functions, and they lie in an infinite dimensional space. And since I have not adopted any parameterization of the distribution, right, it's an infinite dimensional optimization problem over functions. And you cannot even specify that in a computer and solve it numerically. It's even more difficult than a generic, nonlinear, finite dimensional optimization problem. So there are previous work on special instances of this problem. So my contribution here is that, first of all, under certain conditions, which I will state later, I can actually formulate an equivalent finite dimensional convex optimization problem that solves this original infinite dimensional optimization problem. And by convexity, you have all the nice consequences. You have all tractable numerical solutions, and you get the global global optimum. And as it turns out, the conditions actually apply to many resource allocation problems that I shown in the beginning of the presentation. So let me just discuss a little bit about the result mathematically. So the conditions are on the objective function and the generalized moment functions. So it says you can solve it using convex optimization if these two conditions are met. So the first one is on the objective functions. It says this function is to be piecewise concave, which is a pointwise maximum of a finite number of concave functions. And on the right, this is just a visualization of an example of a piecewise concave function in 1D. And there's a similar condition for the generalized moment function appearing in the constraint. So they need to be piecewise convex, which is the pointwise minimum of convex functions. And then here, similarly, I'm showing an example in 1D. So let me just say a little bit more about why these are useful, because if you look at the definition, right, these functions are in general neither convex nor concave. So let's first look at the objective function, which needs to be piecewise concave. So first of all, trivially they contain concave functions, and also piecewise affine and convex functions. So these are constructed by the pointwise maximum of a number of affine functions. And also the 0, 1 indicator function is piecewise concave. And well, in terms of applications, as it turns out, these kind of functions often appear in many resource applications and scheduling problems. And this, remember, if you take the expected value of an indicator function, that becomes the probability. Right? So this is useful, for example, if you want to minimize the system failure rate. If you think of the parameter indicates some kind of failure. And in terms of the generalized moment functions, they need to be piecewise convex. So they contain linear functions, convex functions. So these are used to specify moments about the distribution. For example, mean, second moment, and all the even moments. And also, interestingly, the 0, 1 indicator function is not only piecewise concave, but also piecewise convex. So here, you can use it to specify the tail probability of the distribution. So finally, let me just show the form of the finite dimensional convex optimization problem that solves the problem of finding the worst case probability distribution. So, this part is not important, but the thing you actually want to focus on is the decision variables. So inside here is a pair, so you have P and gamma, and then there are K times L of them, so capital K and capital L. Okay? So as it turns out, these decision variables have a meaning. They actually encode the location and weights of the probability masses in a discrete distribution. So that means the original worst case probability problem, a probability distribution problem, can actually always be attained by a discrete distribution. This is actually surprising. And once you solve this problem, you can just go ahead and from the optimal solution to this problem, find out the worst case distribution, which is discrete distribution and all its weights and locations of its probability masses. So in the following, I'm going to spend some time revisiting the problem that I mentioned in the beginning of the presentation. So now let's do the first example, which is, yes.
So the probability density functions, are they themselves different, or the parameters of the probability density function, there is uncertainty on that? So for example, what I mean is, let's say if you're specifying it by mean and variance, so are the mean and variance uncertain, or it's a Gaussian or chi-square, or?
The last one.
Okay.
Yeah, it's the form of the distribution itself is uncertain.
So how many would you consider? How many such distributions, if the distribution is uncertain?
How many distributions? Mm-hmm. An infinite number of distributions.
Or it could be any distribution.
Could be any distribution that satisfies the moment constraint. So if I give the mean, could be any distribution with that mean.
That satisfies that.
Yes. Gaussian, Poisson, binomial, you name it.
Or you can come up with some arbitrary distribution.
Arbitrary distribution, any form.
Okay.
Not even in a standard textbook of a probability theory. That's the whole point. Yes.
So how do you represent those distributions? As in, I'm assuming that you're using optimization tools. So how would you have to somehow represent it? a finite way, right?
No, that's the main message. So the original problem is to optimize over all possible distributions, and that's an optimization problem. The theorem here says, if I only care about, so first off, I'm not saying that the optimal solution to that infinite dimensional optimization problem is unique. There could be more than one distribution that achieves the same optimal value. I'm saying that the optimal value can always be attained by a discrete distribution, not by a continuous one.
Okay.
Once you get that, then it's a matter of optimizing over the weight and location of the discrete distribution. And also the number of the probability masses, but then, as it turns out, you can also give an upper bound for the number of the probability masses as well.
There is some sort of a mapping from this infinite dimensional system to...
What we say is it's not a mapping, rather a reduction.
Oh, true. Okay, yeah.
Okay, so let me, now we're done somewhat with the math part. So let me start by revisiting some of the applications. So the first application, again, is allocating storage in the power grid. So here I'm going to use a somewhat simple model of the power grid. Okay, so if you have done research in power systems, I'm essentially using a very simple model it's the DC power flow model. So here I'm going to model the power system as a graph. Okay. And for each vertex of the graph, there is some storage associated with it, which is the quantity that I want to assign, I want to make decisions upon. So I will call that xi. And then I put wind power associated with its vertex as well. And now these are the stochastic variables. And then another decision variable that I can choose is the power flow. So if I have, let's say, a lot of wind power generated at this place, and then I can try to transfer them to another place by controlling the power flow. Okay. So in principle, it's a two-stage decision problem. Like, in the long term, you want to decide how the storage is allocated, and in the shorter time scale, you want to decide how the optimal flow is controlled based on the daily basis. And then here I'm just going to focus on the first stage, which is a long-term decision on allocating the storage. So here, my decision variable is my x, which is a vector that shows the assignment of storage across the entire network. And then here I have the worst-case distribution problem, and this distribution is for the wind power generation. So here inside, this whole thing is my cost function. Okay, so you can see this cost function is actually defined by the minimum value of another function. So here it's or you can say it's the optimal value of an optimization problem. And then the optimization problem here it's trying to solve is to control the power flow given the assigned storage to minimize the wind energy wasted. And this is actually also called, to some extent, the DC optimal power flow problem. So as it turns out, so I won't show the details, but this function is actually peaceful concave in detail. So this can be shown using standard techniques in optimization from duality. So let me present the numerical results. So the example that I used is the IEEE 14-bus test case, which is a standard test case in power systems. And also it's a network with 14 vertices, or 14 buses, and then 5 of which are generators. And then I'm going to consider a time horizon of 1 day with a 3-hour interval. So here that means my random vector theta is 5 times 8, so 5 generator times 8 time slots for each day. So it's a 40-dimensional random vector. And then the information that I give about the distribution is just mean and covariance about the distribution. And that is what I obtained from the wind power generation data. So here are the results. So I'm comparing 3 different scenarios. So the first one is that I only give the support information about the distribution. So I only know that this random parameter lies within, let's say, a certain, in one case would be lies within a certain interval, but nothing else. I don't even know the mean of the distribution. So that actually turns out to be equivalent to the conventional robust optimization. It's a deterministic parameter that varies within the ambiguity set. So you can imagine that will give you the most conservative result. And the bottom one is as if I have the exact distribution. So there's a lot of details, but you may imagine that how I can actually get the exact distribution. So in this case, I'm actually mimicking that I have the exact distribution by taking a lot of samples. But here, I'm just the middle one is just I'm only giving the support plus the first and second moment of the distribution. So perhaps surprisingly, so I mean when I saw this, I wasn't expecting this at all. So just by incorporating the first and second moments of this distribution, you can get a lot of improvement from conventional robust optimization, which uses the support information. So the second example that I want to show is in the context of ride sharing. So here, again, the problem that we pose is to how to schedule or how to rebalance these vehicles in order to improve not only improve the service quality, which is measured by the average wait time of the passengers. And certainly, when I motivate this problem, I didn't mention there's another objective we also want to pay attention to, which is we don't really want to move the cars too often to induce unnecessary idle driving mileage. So I have a multi-objective optimization problem, and then I'm just going to kind of scalarize the problem by minimizing some weighted combination of these two metrics. The first term is the cost of rebalancing, which is a function that just depends on my vehicle flows. And the second one is the wait time, which not only depends on my allocation of vehicles, but also the specific demand generated. So all of these are vectors with the corresponding dimensions. So for example, this would be a demand. This demand would be a vector whose dimension is the same of the number of locations. Okay. So the first thing I want to say is why robustness is important in this application. So as a rider, you probably imagine that it doesn't really make too much difference if it waits 2 versus 3 or even 5 minutes. But it really matters if you have one instance that you need to wait 20 minutes or longer. So as it turns out, if you look at the data, so I'm using the exact New York City data set that I mentioned in the beginning. So we use the 4 years of them, so out of 6 years. And for the reason that we use part of the data for making this decision and the part of the data for validation. So you can see that, if you look at, this is the total number of requests plotted against the ID number of that region. Okay. So you can see, especially for this one, like region 3, there's a lot of uncertainty. So as it turns out, if you don't take into account of uncertainty, you can do really, really badly in terms of the high cost cases. So here, it's essentially a histogram. So this is the cost, and this is the number of instances associated with that cost. So here, the green area is the area that we would consider to be really, really bad. Okay. So here, you can see that the non-robust version does a lot worse than the robust version. So by the way, here by robust, I'm just using conventional robust optimization. So this R is the parameter that lies in some n-dimensional, finite dimensional space, and this delta is just the ambiguity set associated with the parameter that I construct from the data set. So the next thing I want to show is how this conventional robust approach compares to the distributionally robust method for this particular application. So here, again, I'm changing my max over a finite dimensional set to a set of distributions. And then I change this to the expected value. So here you can see 4 results. So this horizontal line, dotted line here, is the non-robust approach. And these two, so blue and green lines, are the ones from conventional robust method. And they're different in the way the uncertainty set is constructed. And in particular, the shape of the uncertainty set is different. So one is a box, the other one is more like an ellipsoid. Okay. So you can see that, by the way, remember that for robust optimization, you need to construct the ambiguity set to contain the data point with some kind of confidence or probability. So here, there's a naturally associated with this confidence level. So I would rather call it the level of unconfidence, just because actually 0 means that you contain all the data points with 100% confidence. So anyway, so you vary this, and then you get different results. So you can see that if you kind of tune the parameter properly, then both of these robust methods will outperform the non-robust one, which just make decisions based on the sample average. And then here, finally, this kind of horizontal line below is the result from distributional robust approach. So here, I should admit that this is a partial result in the sense that although in principle in distributional robust method, you still need to tune this confidence interval, because that you need to contain the probability distribution with certain confidence. But here, we're not, I think this is chosen to be epsilon equals 0.2, if I remember correctly. So without even optimizing over the confidence level, this is already getting very close to the best possible robust optimization approach that we have. So let me spend a little bit more time discussing about the future directions. So first of all, I would say the ultimate goal for all of this is to build a system that will eventually run in real time without any human convention that turns data into useful decisions for complex systems. That's the holy grail. And the reason that I want to get performance guarantees is that I think that's important for reducing human intervention. Right? So if we think about the state of art, in most cases, there's a human operator sitting somewhere in between. So there are a lot of data analytic tools, and also they're also often accompanied with visualization, just because their results often needs to be interpreted by some human operator, and based on those results, the human operator will make decisions. So this is not an entirely automated process. Right? So as basically you're limited to the reaction or the response time of the human operator. So the holy grail, I would say, would be, so once you get to once you can get some performance guarantee for a decision-making system, then eventually the hope is to get rid of this human operator sitting in the middle without, you don't have any intervention of you. So I think I'm listing a few directions that I imagine could push the state of art to the holy grail. So the first one is the possibility of dealing with large data sets. So here, I should admit that for all the results that I have shown, they're done in offline. So even for the taxi dispatch problem, I'm just using the remaining of the data set as my validation set, but they're definitely not run in real time. And currently, yes, I did that in MATLAB. However, there's, for the current method, I don't believe it will just can be directly implemented and used in real time. Right? So when you do this, then some of the techniques that can be applicable, for example, to the distributed computation, or you don't compute the result exactly, but rather use some approximation algorithms. And the second thing, which I think is also related to large data set, or in terms of helping the algorithm run faster, is to exploit some structure of the underlying stochastic phenomenon. So right now, if you think about that wind power generation example, as I said, I'm just modeling the spatial temporal phenomena of wind power generation as a random vector. I take the product of number of locations I take with the number of time slots, and that's my dimension of my random vector. Well, the nice thing is that I don't need to put more assumptions, and I'm not, and the algorithm doesn't require me to put more assumptions about the distribution. But I'm actually also perhaps ignoring a lot of useful prior knowledge about the distribution. For example, Markov properties. But the question is, what is the proper way of incorporating those prior knowledge into the distributional uncertainty? And that may also be a key factor in speeding up the algorithm to make it run in real time. And in terms of running in real time, there are other things to consider. For example, when to discard older data, when to relearn the system, how often you refresh, if you will. So this is the last slide. So I want to summarize.
Can I
yes.
add something with the Markov properties? So you're
Yes.
assuming that there is some form of logic in this stochastic.
I'm not sure if it's logic, but I would still call it prior information to be general. But for example, Markov property could be it could be both in space and time. So the wind power generation could be one instance of that, at least maybe in terms of
But the
time.
inherent assumption is that there is some properties of how wind is blowing that you will be able to.
Yes. Like this is more getting into the kind of art of modeling, like how much prior information you want to give to your model. I think the Bayesian or frequent is the argument. I think the general consensus is that if you're a domain expert and you know a lot about the underlying phenomenon, and it is often helpful to incorporate your prior knowledge into the modeling so that you can actually get better performance.
Do you get rid of the stochastic nature of the distribution?
No. You still say it's stochastic. It's a distribution, but it is not any distribution, for example, that satisfies my moment constraint. It's any distribution that not only satisfies my moment constraint, but also satisfies my structural constraints.
So this reduces your set of distributions. So
Yes.
It makes them proper.
So for one example that I can give you, which is not shown here, is to impose that the distribution is unimodal. And that then can actually be imposed. And that is the special instance of the structural properties. So I'd like to summarize. So in this talk, what I presented was to capture data that are samples from an underlying probability distribution as a distribution uncertainty. And this kind of uncertainty can be used in terms of making decisions. And then the good thing about making use of this distributional uncertainty is, first of all, you preserve the kind of distribution information, and also you have the worst case design, which is important for some of the engineering applications like ride sharing. And then not only this, under certain conditions, making use of this distributional uncertainty, although it seems hard because you're optimizing over infinite dimensional space, but in certain cases, this can actually be made computation efficient by turning the original problem into a finite dimensional and convex optimization problem. And this condition, as I showed, can actually be applied to a large class of problems. And then, for example, some of the resource allocation problems, including ride sharing and allocating storage devices in the power grid. So I'd like to finish here and be happy to take more questions.
Very nice and smooth presentation. So, have any questions?
Just curious, when you in the problem of the minimax of the expected objective function, do you concern about the variance of it or covariance of the objective function?
Oh, I see. That is actually a very good question. So it's the short answer is that the result will change because all the conclusions that I have given you depends on the fact that my objective is a linear functional of the distribution. So if you incorporate, like you're doing like something like a risk management, right? In some sense. So I'm, for example, minimizing or trans-constraint optimization. So I'm doing the weighted my objective function could be the weighted combination of my mean and covariance or variance, and then in that case the conclusion will actually change. and that becomes a much harder problem.
Okay. Thanks.
But but I'm not saying that is not important, because the expected value is not the entire story, of course.
Okay.
Yes.
So, do you make any assumptions on the samples that you're getting? Because it's when you don't restrict the space of probability functions, I have no clue what the actual probability distribution is. So, why should I even believe the few samples that I have? I mean, the actual distribution may be normal distribution, but I may be getting all degenerative samples, right? So I'm kind of curious to know what are the assumptions that you place on the samples that you get.
So the assumptions on the samples is important when you construct your ambiguity set or the distributional uncertainty set. And for the way that I presented, the assumption there is that they need to be independent. And of course, identically distributed, because I'm assuming they're coming from the same distribution. In that way, so the reason that I require that assumption is because I need to relate the size or the diameter of my ambiguity set with the number of samples. Of course, you can imagine the larger the number of samples is, the smaller my diameter would be. And this relationship, which is given by classical probability theory, hinges on the fact that the samples are independent.
But wind is correlated, right? I mean,
Yeah.
Okay, so that's an extension. I think weak correlation could still work.
okay.
Weakly correlated samples. But I mean, everything you know about probability theory just apply there. It doesn't affect the optimization procedure later. So it only enters at the stage of constructing the set. But here I'm not really getting into the detail of how to construct the set. It's things from there on.
Anyone else? I have two. So I guess you covered it, but what makes it convex?
What comments?
The formulation. So why is this problem convex?
Oh, okay. Let me actually go to that one. Okay. So this is now it's a mini lecture on convex optimization. So we're optimizing the decision variables are p and gamma. So my assumption is each f super k is concave and each g super L is convex. Okay. So let's look at the objective function. So this is a perspective transformation. This is on the convex function f. So this has a form of p f of gamma over p. And the perspective transformation preserves convexity or concavity.
But
So
why is it convex? Why is f convex to begin with? Is the question.
Oh, I see. So that's the condition.
But is it? That's your assumption, right?
That's the condition in the theorem. So I said
But is it real for the systems that you study?
yes. So I mean I haven't shown this. For example, here I didn't for simplicity I didn't really show the form of this cost function. This is actually so for the DC optimal power flow problem, you're essentially solving a parameterized linear program. Which means it's a linear program whose constraints contain this parameter of interest theta. So theta appears in the constraint of the linear program. So if you use duality, then you can show that this function itself is a pointwise maximum of a number of affine functions, which is this case I presented.
Yeah. And second question is it important to get to a global solution? Do you get a global solution, or I know you published in the global optimization.
Yes. Yeah. Okay. So here's my argument. If you can get global solution easily, then why not? My second statement would be yes. For many of the problems that I studied, they're high dimensional. So getting global optimization, getting global solutions without convexity can be computationally very expensive. So in both ways, convexity or global solution is important.
So what solvers are you using for the max-min problem, for instance?
It's Sadumi. Okay. So I think for most audience, I should say CBX. Yeah. But CBX itself is not a solver. It's an interpreter. It's a translator. The translator problem into the canonical form that can be handled by other real solvers. For example, CBX itself does not do any Newton's method. So that's in that way, it's not qualified as a solver.